joules per kilogram Kelvin temperature relationship. In other words, it takes 4,000, almost 4,200 joules to raise the temperature of 1 Kelvin of water, or 1 kilogram of water by 1 Kelvin, 1 degree Celsius. If we were to express that number in a little more user-friendly, lab-friendly units, it would be 4.186, or about 4.2 joules per gram Celsius. Again, Celsius and Kelvin meaning are implied the same thing in this context only, is the temperature change idea. Now, originally, the origin of measuring or explaining heat capacity was to start by saying, well, we can use water for just about everything. We use water to establish a temperature scale. We use water to establish density scales, things like this. There were lots of things we use water for. It's ubiquitous to chemistry, certainly biological processes, et cetera, et cetera, et cetera. Well, the original interpretation of heat capacity, when it was first identified that, oh, it takes less energy to heat up metals of the same quantity as it does to heat up water. And using water, because of its utility in the laboratory, as well as its ubiquity and its relationship to temperature in the Celsius scale, it was originally established as a relationship with the amount of energy in calorie units per gram degree Celsius. And to give you a sense, the original concept of the energy unit in calories, which was defined in terms of water, one calorie corresponds to the energy required to raise arbitrarily 1 gram of water by 1 degree Celsius. Talk about arbitrary. But it gives us a measurable standard. And by this standard, then, the specific heat capacity for water corresponds to about 1.000 at around 20 Celsius calories per gram degree Celsius. So 3 different unit systems to describe this quantity. This one's particularly helpful because it establishes fundamentally the relationship between, the relationship between heat energy and temperature in a physically observational sense. And this heat capacity, and that'll be relatively important. To this end, though, if you note, in joule units, in a gram per Celsius sense, or a calorie per gram Celsius sense, this implies a fundamental relationship which was paramount in starting to tie the ideas of heat and mechanical energy together. The establishment that 1 calorie corresponds to 4.186 mechanical units of energy, the joule, was one of the fundamental.
Isn't it?
4 or 6, depending on the textbook.
I thought it was something slightly different than that.
So James Prescott Joule, not to name drop, was the individual that actually did experiments to measure this. He took measurable work experiments, basically taking a mass and allowing it to drop and measuring the work associated with gravity doing that. And at the same time attached this falling mass to a contrived blender system. So you could agitate water and measure temperature change in the water. And what he found was that this many mechanical joules always corresponded to in a heat sense, pretty close to a 1 calorie energy transfer, or heat transfer. A beautiful set of experiments that he did in, I think, around the 1870s. And obviously profound, because heat was not previously understood as energy in the sense that we think of it now. And mechanical energy was simply a integration sum of force and displacement. And so these were very disparate ideas. Okay, so that's the idea of this heat capacity. We have mass and temperature. Now, here's the thing. When we talk about temperature change, heat transfer specifically, this corresponds to something else that I implied a long time ago, like maybe 1 or 2. This corresponds to thermal energy increases or decreases, because temperature is directly related or proportional to internal thermal energy. Forget about expansion. So heat that is absorbed in this form represents changes, increase or decrease, in thermal or internal energy within the system. In other words, the atoms, molecules start vibrating more, bouncing around more. It's a gas. So this is an important one. This is not the only heat. This is when energy transfer is observably related to temperature change. It's only that component of energy transfer. Okay? Now, I will also point this out. This means that the internal thermal energy, if you will, random energy, changes. When temperature changes, or when T changes. Okay. Again, it's not the only one. Now, let's look at the other one that we talked about in terms of thermal energy transfer. Thermal expansion. The other possibility, and they may in fact be intertwined, is that heat absorbed can result in changes in volume. And that may be by just having a shaft that increases linearly in dimension or increases in all dimensions. Take a balloon, put it in warm water, and expand a little bit. Heat associated with volume change. Anytime a volume changes, think about what has to happen. We use linear thermal expansion. We talked about this a little bit last time, but let's just think about this for a second. We have some system, and this system has a certain volume, and that volume is based on the cross-sectional area and this initial length. So V naught would be whatever this surface area is plus L naught. Now, as this system absorbs energy, so you get a certain amount of Q coming in. Some of that certainly will change the temperature, but as the temperature rises, we know that there's this linear thermal expansion, or this volumetric thermal expansion. But here's the thing. In order for this to expand and say, increase in some direction like this, these molecules have to push against something. What do they have to push against?
Gravity and atmospheric pressure.
At the bare minimum, atmospheric pressure. So we have pressure pushing down, we call it atmospheric pressure. And we have associated change in length. Well, we can express pressure in terms of atmospheric force pushing down times surface area. In these terms, as this thing expands, we can note that the work associated with this expansion, delta L or delta V, will be related to the force that it pushes outward against the force that's pushing back. If it increases at constant velocity, then the force in the surface area outward corresponds to the force pushing back the atmosphere. Just think at the surface. I'm saying this backwards.
I was gonna say, isn't it?
I'm saying it, yes, I am saying it backwards, please forgive me. This is force per unit area. Sorry. So what we're left with, though, is we can think of force, which is pressure times atmosphere, or area. We can think of this as times delta L. It's pushing upward if we ignore the side directions. It's pushing upward a distance, delta L, against a constant atmospheric force. This atmospheric force corresponds to pressure times the surface area times delta L, and I'm leaving the integral out and just keeping it simple. This corresponds to pressure times the change in volume. Heat associated with volume expansion or compression. Here's your volume expansion or compression. Corresponds to the work the system exerts on its environment. It's how much work it does to push against the atmosphere physically in order to expand. If it were in a vacuum, it wouldn't have as much effort to push against. But if it's not in a vacuum, then you've got this atmospheric pushback or opposition. So this Q, this change in volume, corresponds to the work associated with that volume change. And this quantity corresponds to pressure, because it's pressure that the system has to push against, external pressure, times change in volume. And we can write this as a differential, but in its largest, sort of most complex form is this. So now we can sort of reinterpret this. Whenever you have heat transfer, energy transfer into a system, system's temperature can change, and simultaneously or not, you may have an associated volumetric change, which also requires energy. You cannot do work without that energy coming from somewhere. So some of the energy absorbed has to physically be involved or transformed into mechanical work. This is the whole idea about lifting a 5 kilogram mass. That would be the atmospheric pressure plus this quantity. Okay, it's very important. So together, and there may be other forms of work, but these are, or I'm sorry, heat exchange. But these are sort of the big ones. So what we're left with then, and this can be summarized in a very simple form. So for any closed system, we can say that the net heat gain or loss, we call it Q net for now, will correspond to any heat associated with temperature change, and that's again observable, and any heat associated with work or volumetric change. Okay, it doesn't matter what's pushing against it. If it's expanding a certain volume, if you know what the pressure is associated with atmosphere, any other external pressures, you add that pressure, you establish what the total pressure is, and you multiply that by the volume change. And that is the mechanical work. That's a little bit subtle, because this is the work by the system on something else. We're no longer worrying about a ball with Joey pushing on it. Now we're worried about how the ball, or how, instead of worrying about the ball and work being done on it, now we're worried about Joey and the work he's performing. And so we're making a very subtle industrial perspective change. Not what's happening to things, but how things are able to exert those disturbances. We can rewrite this, by the way, in another form by putting these other pieces together. We can say that heat gain, and now by the fact that there is a heat transfer, we are talking about a thermal process. Even if there's a mechanical process attached to it, it's a thermal process. It's related to internal energy change and any energy associated with work and volume change that happens simultaneously with that change. In other words, we're just accounting for the energy. We're all the way back to chapter 6, and my little quote by Feynman, what is energy? Well, we don't know necessarily what energy is. We just know it's a number that we can always account for all of it for some reason. And these numbers always add up. Don't know why per se they add up, because they come from different organic origins, mathematical, physical origins, but they always add up. And so this is a particularly important relationship. And this is referred to as the first law of thermodynamics. It's another statement of energy conservation. Big ticket. Translation for us. It's basically Newton's second law for thermal problems. It's what you have to solve analytically in order to solve a thermodynamic problem. Everything is based on relationships to this. There's all kinds of other philosophical, abstract tie-ins. But this is what this is the mathematical problem, solving this expression for systems where there's heat transfer. And even when there's not sometimes. Okay? So that's kind of an important thing to take away from it. So you kind of see how this fits together a little bit. It's like a ledger sheet with accounting for things. Just like we account for forces, we describe, we know some forces, we don't necessarily know everything, but we do know the physical response. Just trying to attach causality to otherwise unknown but inferred ideas. Okay, I didn't mean to erase this because we're informed, but there's one other type of heat exchange that is not specifically established here yet. And this happens without specifically the temperature change. And there isn't necessarily an associated work involved. There is, but it's a little more subtle. So I guess this would be item number 3. So I guess I'm going to put that back in there. And make it one of this by system. Right. You're using energy to do work. Thermal energy, burning gasoline caused pistons in the automobile to do work. Okay, so now we're talking about the machine, not the thing that's being moved by the machine. The third is It's what happens when you have change of phase. And the other possibility is that you can get a phase change. And this phase change can happen at constant temperature. Easiest example is take a glass of water and stick it on the table at room temperature. Given enough time, you're going to get a very, very slow evaporation without a temperature change, because it's in equilibrium with its environment. So it can happen. It can happen when you freeze, when you boil. It can happen even when you're between these critical states of a system. And the heat associated with phase change, well, how much matter physically goes from solid to liquid when heat is absorbed? Well, the amount of heat depends physically on the amount of mass that undergoes that change. So I'm going to say, call it delta and delta. In other words, you start with you have a, say, a 1 kilogram sample of water. And maybe it's in solid form. Then you have heat, I'm just going to call it phase, that results in some fractions, say 0.1 kilograms melts to liquid. The amount that melts is the 0.1, not the total. Though, if you wanted to know how much energy would be required to melt all of it, you would use the total. But here's the thing. All substances, when they're in any particular state, have a certain interaction with their neighboring molecule, or mass particle. Consequently, the energy required to break things apart and shift things around to cause them to completely change from one state of matter to another depends on the type of system or the type of matter that's present. And so we have another intrinsic physical property. This one's referred to as the latent heat property. We'll use a letter L for that. In this case, L is referred to as the latent heat, or latent heat constant. And there are 3 different types. Well, there's actually probably, you could think of it, you could stretch it and say there might be 5 different types, but at the very minimum, there are 3 different types of latent heat constants for most substances. There is the solid to liquid latent heat property. In other words, how much energy per kilogram is required to melt water, a certain quantity of water. Or how much energy must be removed from a certain quantity of water to freeze it, without temperature change necessarily. This is called the latent heat of fusion, or LF. The solid to liquid process, whichever direction it goes, it's the same quantity in either direction, called the latent heat of fusion. I'm going to write all of this now back. And the units would be in joules or calories or whatever per kilogram. Okay, it takes a certain amount of energy per unit mass to melt or cool or freeze a particular substance. There's also a different value, but a characteristic liquid to gas latent heat. And this is called the latent heat of vaporization, or LV. Again, the units are joules per kilogram. But the these numbers are not necessarily, there's absolutely no reason why they need to be equal. Interaction between water molecules in liquid state when you're stripping them apart to evaporate, different interactions than you have between the solid ice molecules that are attached to each other and the liquid state. They're completely different. Highly dependent on temperature, highly dependent on atmospheric conditions. It takes less energy to boil water off or evaporate water at very, very low pressures because you've got nothing pushing back against it. And there may be an associated work involved with volume change. You physically have to displace when this happens. So there is a little subtle work involved as well. The other, which we don't see so often, but it's the dry ice effect, or it's freezer burn. There's a reason why when you put food in the freezer, you want it to be vacuum packed with very little space between the packaging and the food. Because if there's any open space, even if there's not, it can still happen. You get sublimation. And then the reverse. Sublimation is when you go from the solid to the gas state. Dry ice. Put it in water, it fumes off. And then, the reason you see ice crystals is after it's sublimated, it then redeposits because it's at a cold temperature. And now you have ice crystals on the surface. What was water inside the material, the cellular structure, now is water forming these ice crystals, indicating freezer burn. And then you have this dried beef jerky looking crud in your freezer package. And that's the latent heat of sublimation. Again, it's in joules per kilogram. And by the way, it's also the reason if you just put ice cubes in the refrigerator, in the freezer, they're nice, big, and fat, but over time, they shrink. As you get the ice crystals forming along the outer edges and the inside of the refrigerator, it happens, or the freezer. So it does happen. It doesn't happen as quickly as the freezing process, but it happens. It's there. So this is latent heat of sublimation. So now this one is typically sorry about that. It's not a I'm not a Mets fan, so it wasn't subliminal. I just left out my L. Go Sox! Sorry. Okay, so we could add that, if you will, to this then as well. If there is in fact a change of state. Now, this is not explicit in your in the textbook, but there is in fact the potential to have change of phase. And I'll just call it Q delta phase. Normally we refer to this phase change in terms of chemical energy change as well. So there's some subtleties built in.
So if there is no phase change, it just drops?
Yeah. Yeah, so anytime we have a system where we don't want to worry about it, and when we get to sort of thermodynamic processes, we will not concern ourselves with it. But technically it's there. Again, it's just one more thing to account for. Now here's where it kind of gets interesting. The way your refrigerator works is that you have this constant liquid to gas process undergoing. You start out with a liquid, you warm it up, or you expand it rapidly, you get a gas. If you heat that gas up, then you can compress it really fast, get a liquid, remove the heat, cool it back down, and keep the process going. So refrigeration systems are much more complicated than the refrigeration type of devices thermal transfer we'll talk about. But there is this, in addition to just energy transformation, there is this heat transformation of phase, which is huge. That allows us to make our refrigeration system so efficient, or as efficient as it can. Okay, so everything else is about putting these pieces together in any possible way we can. Because we can define sort of our mechanical universe, at least when it involves heat, energy transfer, in terms of that basic expression. By the way, there's another term here that you may have heard. Chemistry, how many got chemistry again? A couple, not many. Sometimes we call this term here enthalpy. And if we're thinking chemistry, there's one more thing that you might want to throw in here. What else can happen when you take, say, water, or let's take hydrogen and oxygen, put them in a big blimp, accidentally spark it? What happened?
Combustion.
You get a chemical change as well. There's energy associated with that. It may be heat in, it may be heat out. But there's also, if we wanted to add it, and I'll put this in green again because it isn't always necessary, but there is also energy change, chemical energy change. And chemical energy change depends on how much of a given substance physically transforms, or multiple substances, into something new. So there's also this as well. Okay, so we're not going to deal with chemical processes, but whenever you have chemical, and this is related to another term from chemistry, which is probably, it's notably named after the most important physicist that almost nobody ever talks about in physics, J. Willard Gibbs. It's sometimes referred to what we call the Gibbs potential, or the Gibbs energy. Gibbs is also the individual that sort of pieced together the lattice of vector mathematics for us. And he just did it, I won't say on a lark, but kind of like me teaching this class, he just needed a way to put relationships of fluid mechanics together, and so he just worked out some vector relationships and completely redefined our mathematical process at the same time. And he did it at Yale, which was a far reaches, cow town, small podunk school. We don't think of it that way now. It's Yale. It was a time when it was the outskirts of anything useful. Okay, so that's a lot of thermodynamics. By the way, any other energy changes that you could ever possibly account for? Slap them right in there. Add another term, another term, another term. If there are other processes that can't be described by those things. So see what I mean by a powerful tool? It's not an easy tool to solve, but it's a powerful, powerful tool in any mechanism. Could be money, could be finance and expenditures. Use it in a lot of different ways. Okay, so this is everything that we're going to pretty much be talking about over the next week and a half. So I cannot overstate the significance of these ideas any more than Newton's second law can be overstated. It's impossible to overstate. So let's look at, let's pick a system. Let's pick something other than here's one. Pressure cooker effect. Just making crap up in there. Pressure cooker. So we're going to take gonna take some sort of a container. We'll assume the container itself does not have an effect on the system. And we're gonna fill the container with, let's keep it simple, how about a kilogram of water? And I gotta be careful here because a lot of things change when you start making up problems like this.